hash value. Okay? So only the source and destination can really access the or compute the correct hash value. So now I also said in that so you can have two kinds of, so before that, so I said what, the IPsec doesn't require any change in the higher layers. So you may think that to use IPsec you have to change something in the transport layer or an application layer or anything like that. No. So it's just an add-on. And after the IP header, you will attach the IPsec header. So typically in a packet you have IP header followed by the transport layer header. And IPsec header and then the data. So now the IPsec header will be kind of in between the transport layer header and the IP header. Right? So depending on what you want to provide, confidentiality, integrity and authentication, you can have two kinds of IPsec headers. One IPsec header is an authentication header. So by authentication header, and I said you can actually get both together. So an authentication header provides you integrity plus authentication. Whereas if you go for the encapsulated security payload header, you get all the three: confidentiality, integrity, and authentication. So with this, you cannot get confidentiality, only integrity and authentication. Whereas if you go with this header, you can get all the three. Okay? So that's what we are going to see now. So last time I started looking at the IP, the header. So this is a standard IP datagram, right? I told you the terminology, so I'm familiar with it here. So this is IP header along with the whole thing is called a datagram. Okay? So what I show here is the structure of a datagram according to standard TCP/IP protocol stack. Okay? So this is the IP header and this is the TCP header and then the data. So the IP header has several fields which we not go through in this course. But there are fields which do not change. So this is basically put together the source, sent through every intermediate network, forwarded by the routers, and then processed by the destination. Of course, then IP header should have what? The source IP address, who is sending it, and who is receiving it, right? The source and destination IP addresses. And I told, I think, at the beginning of the class before last class, what? The contents of the IP header don't change, right? And the contents of the TCP header also don't change, most of the contents, right? There are some contents which change. One content that does change in IP header is called the TTL field, which is basically like keeping track of the number of hops the packet has gone through so far. So it will be set to a maximum value by the source, typically it's 8-bit field, so it could be like 255, that's the maximum value with 8 bits, or 127 or 128. And it is decremented by every router as it forwards. And if it reaches 0, the packet will be dropped. So we don't want a simple security attack would be someone can put a packet. So imagine like if you're sending a postal mail to an address that doesn't really exist, right? So what happens? If every post office keeps forwarding to some post office in the hope that they'll forward it to the right address or something like that, then the mail will keep on going forever, right? So we don't want such a kind of attack. So that's the reason why we have this field that is used to limit the number of hops the packet can travel. Okay, so it's part of the original IP header system. So it's not really something IPsec does. Original IP header already has this TTL field. Okay, so that field changes every hop. And if you have heard about fragmentation, where if a datagram cannot fit within the maximum allowable size of a packet within a network, it has to be fragmented. Okay, and sent as multiple fragments. Fragments independent datagram that travels through the network, the subsequent networks. Okay, so those fields that handle fragmentation change, right? And so the rest of them in yellow, the first is type of service. So type of service could be something if you want the routers to update. This is mostly if you want some quality of service like video streaming, you're subscribed to kind of service provider, and your packets need to be given some quality of service compared to other packets in the internet which are given some best effort service, right? So you could update the type of service field. So those fields could change in every router or some of the routers. But the other one, the yellow, typically source IP address, destination IP address, and the packet header length and packet length and all these things will not change. Okay? Alright. So now if you also notice the standard IP header that I told last time, there is this protocol field. This protocol field indicates what is the next header or the next protocol that needs to process this packet. So after the IP header, the standard packet data graph, it has to be forwarded to the transport layer protocol, the TCP protocol. Okay? So imagine it's a layer of protocol stack. So you have the application, and below the application you could have several transport layer protocols running. So TCP is one of them, UDP is the other. Even you could have IP and some other cases you have IPX. This is nothing to do with IPsec. This is some novel, if you have heard of this company called Novel, I don't know if they're still running or not, but they propose this IPX as the networking protocol for their networks. Okay? And then Ethernet or Wi-Fi or any link level technology. Okay? If you've heard of ATM, heard of token ring, all these things are link layer technology. So all these things are protocols at each layer. So it's a protocol stack. So you should know from a networking class that each layer is just providing a service to the higher layer. So I also told the link layer protocols help you to forward a packet from what? One network to or within a network basically. So if I want to send a packet from this source here to the destination here, I could be running Ethernet here, Wi-Fi here, I could be running say token ring or some network protocol here, or the link layer protocol here. So if I want to send from this source to this destination, you have to use your IP address of the source and IP address of the destination in your IP header packet, right? Whereas how the message physically sent depends on what link layer technology is used. So Ethernet, you might know, it's a shared bus. So you have to handle the collision and all the stuff. So, and then once the packet reaches this router, it is sent according to the Wi-Fi protocol. From this router to this router. So Wi-Fi is what? The basic IEEE 802.1. I get of this. And then from this router to the destination, you could be using a token ring network. So it's a ring in which the token goes around, and whoever has the token can send the packet. So what it means now? So how the packet gets forwarded from from the source across its routers to the ultimate destination doesn't really depend on the underlying networking technology, underlying link layer technology. As long as the packet gets transferred across every hop, it is fine. So in one hop it could be through Ethernet, and one hop it could be Wi-Fi, and one could be token ring. So as long as they provide the service to the higher layer protocol, it's fine. Okay? Similarly for the transport layer, so transport layer is concerned about the processes, right? So there's a process running here, actually sending the message to a process running at the destination. So for the two processes, they don't matter actually whether you send through a best effort service IP or IPX or anything that is available at the networking layer. Okay, they don't even care about the path the packet takes. As long as the packet sent by this process reaches the process destination, that's fine, right? So at each layer, you're just providing a service to the higher layer. How that service is provided, the higher layer doesn't care about it. Okay? So from the transport layer protocol point of view, it doesn't care about the path taken by the packet. Similarly, from the networking layer point of view, it doesn't care about what link layer technology is used to send the packet from one hop to the next hop. Okay? So why I said that? So now as the packet goes through the stack, I say at the destination, so once the packet is processed at the IP layer, okay, the IP header, you need to know to which protocol we have to send. So if you work, we have seen in offices, after that particular office for process the file, they'll put some note telling the next officer should process this to be this office number or something like that. So the back file will be forwarded to that office and then we can go on. So like that, there is a protocol field, an 8-bit field that tells you what's the next protocol that needs to process this packet. So in a standard packet, the next protocol field will be the TCP header. So each next protocol value will have a code value. So it's 8-bit field. You can go from 1 to 255. So for TCP, the standard value is 6, and for UDP it is 17. So now if you want to indicate that the next header following this IP header is not TCP header but an IPsec header, the next protocol field should have the value that will indicate that's an IPsec header. And given that we have two kinds of IPsec header, an authentication header or an ESP header, you need to know the protocol values for them, right? So the protocol value for the authentication header, what we saw last time, 51. Okay, if you look back at some previous first slide on IPsec, authentication header, the protocol value or the next header protocol ID is 51, and for ESP it is 50. Okay. So that's the value that goes here. So it's kind of like a linked list. So which means after the IP layer process a packet, you should go to the IPsec layer where you have the authentication header, right? So that needs to process this. And so now let's look at the authentication header. So how does it look like? Now, one thing also, the first thing that you notice in authentication header is what? The next protocol field. So why we know the next protocol field? After the packet is forward processed here by IPsec protocol, it needs to be processed to forward to the TCP header. So if you see this, the next protocol field actually says TCP. So TCP means the protocol value should be 6. Okay, so it's a linked list from one header to another header, how they should be processed. Okay, so now let's look at this particular authentication header, which is of interest to us. So it contains the next header field and then the payload length field that indicates the length of the whole authentication header. So like the authentication header has the sequence of fields. It's not two-dimensional, again it's all one dimension, but just to represent it in more structurally non-visible format, we just break it as 32-bit rows like this. Okay? And so the length of the whole thing so in 32-bit words, so which means here it is what, 4 words, so each 32-bit quantity is a word. Okay? As you notice here, the first 3 cannot be more than, like each one can be 32 bits, like this can be 32 bits, this can be 32 bits. The last one would be more than 32 bits. Okay? So we'll see each of them as we proceed. Now this is reserved, so it's not being used. Okay? Now, I introduced this term last time, security parameters index, right? What does it indicate? It uniquely identifies an IPsec security association. Okay? So, the sending say from the, and also I said what? IPsec security association is bound by direction. So, if you want to send something from, actually then there's no concept of source and destination actually. So if you want to send something from A to B, there should be an IPsec security association that is outbound at A and inbound at B. But if you want to send something from B to A, there should be another association established that is outbound at A and inbound at B. So whoever is sending is going to send it outbound and inbound at the destination. Okay? Now, so that is used to indicate, so each security association is identified with a unique SPI value that's actually only locally unique. Why it is just locally unique? Because this host may have several security associations with several other hosts out there. So to distinguish between the different security associations, you need to have a unique SPI value. So the SPI value of a security association along with the IP address of the host makes it globally unique, because each host has a locally unique SPI value and each host has a unique IP address. So the whole thing uniquely identifies a security association. Okay. So if you put yes.
Dr. May, you got a question that says something similar to what the common characteristics. Is this what you consider to be the common characteristics?
I can't hear what you said.
One of your questions for exam 3 is what is the common characteristics of an authentication header? Is this what you consider to be the common characteristics?
Not this one particularly. Authentication header mainly provides you integrity and authentication. So that is its common characteristic. That is one characteristic. It provides you integrity and authentication.
So those are the common characteristics that you're talking about?
That's one of the common characteristics. So as we talk about, you can note down the other characteristics too. This is one of the characteristics. Okay? The SPI value is something that I told last time is uniquely identifying an IP security association. Either use authentication header or ESP header, you have to go to the security association. Okay? Now, the next one is sequence number. The sequence number is like for every packet you said 90 sec header to 35,000 packets, you increment the sequence number from 1, 2, 3, 4, so on, so nothing beyond that. Okay? So it's a 32-bit quantity, as you see here 32 bits. So the sequence number can go from 0 to, or it starts, I think it starts from 0, so 0 to the power 32 minus 1. So after sending that many packets, if you still have some packets to send on that security association, you have to kind of terminate the current association and establish a new security association. So this is again to prevent something called a replay attack. So you don't want two packets with the same sequence number reaching the receiver. So if you terminate the current security association and open a new security association, what will change? The SPI value will change, right? Because each security association has a unique SPI value. So if you terminate something and you open a new security association, it will have a new SPI value that will identify the security association. So then, what are the packets you send on that will have again starting 0, 1, 2, and so on. But since SPI value changes, that along with the sequence number will kind of uniquely still identify the packet. So there cannot be any chance of a replay attack. Okay? And then the authentication data. So this is a key thing here because we want to provide integrity and authentication. So how does what is this? Basically hash value. Okay. So for the data that you have, for the data, like you see, that's why I highlighted everything in yellow. Those are the fields that are used to compute the hash value. So since you know the, if even one bit changes on the message for which you're computing the hash value will change, right? So that's why we are using only those fields that will not change all the way from the source to the destination. So that is another characteristic. So what fields are used to compute the hash value? Only those fields that are not changing from the source to the destination. Like I said, the details will change, the fragmentation fields will change and all those things. So we don't want the routers to compute the hash value because they are not part of the security association. Only the source and destination are part of the security association. So the data doesn't change, the TCP header doesn't change as I just described, and most of the fields in the IP header doesn't change, and the fields in the authentication header also doesn't change. So all these fields are used to compute the hash value. And the hash value is computed based on a keyed hashing algorithm. So both the source and destination have to be given a secret key as part of the establishment process of security association. And once they establish the association, they know what algorithm and key hashing algorithm and what key to be used. And using that, they'll compute this hash value. Okay? And the receiver has to also do the same process. So all the it has to use all these different fields and recompute the hash value and see if it matches. If someone really messed up with the data or just trying to change something in the data, the hash value should not match. Or even if someone tries to change the source IP address and makes it appear like a spoofed IP address, the destination can verify it because it knows the right key used to compute the hash value. So no one can, it's possible someone can put a fake hash value, but the hash value will not match with what the destination will compute because it doesn't, the intruder doesn't know the key to compute the hash value, while the source and destination know the key to compute the right hash value. Is that clear? Mm-hmm. Now there's a padding required if the hash value not a multiple of 32 bits. So that's why you see here it's a variable. But if you try to make it like aligned with 32-bit boundary, so if your hash algorithm use a hash value that's only 30 bits long, you may need some 2-bit padding so that it's a multiple of 32 bits in the packet length. Okay? So that's with the authentication header. It provides you only integrity and authentication. So now if you want confidentiality along with it, then we will use the ESP header. Okay? So with ESP header, so again you have the SPI value, the 32 bits, and then the sequence numbers, that's the same. Now the thing here is the way, if you look at the authentication header, how it is used is a kind of inserted very simply between the IP header. So this part is your IP header, and then you have the TCP header here, and then you have your data. So the way authentication header is inserted in between the IP header and the TCP header is exactly like what I have shown here. Okay? But if you look at the way the ESP header is inserted, it's kind of little kind of not that straightforward to look at, but it's quite easy to understand once you know how it is done. You see here, this is the standard IP header, and the way it is, the ESP header includes the TCP header as well as the data. Okay? So the ESP header includes or kind of engulfs or kind of includes the TCP header as well as the data. Okay? So the way then it is so you have the first two fields, the SPI field here and the sequence number field, the two fields I just showed, 32-bit quantities, and then you have the TCP header and the data. And then you have the rest of the fields of the ESP header. So it's not like one contiguous, like an authentication header. Everything that is part of this header is corresponding to the authentication header, right? Nothing was for TCP because the TCP header was standalone, separately following the authentication header. Whereas the ESP header, some fields are for the ESP header, and then you have the TCP header and the data, and then some more fields for the ESP header. Okay? And the rest of them, the whole thing is for the ESP header, not the ESP header. Right? So that's what we're going to look at. What are those fields? So the SPI sequence number, and then you see the payload data. So the payload data that is shown here is actually the TCP header and the data. Okay, so it has nothing to do with your ESP header. And then, as I said, there's some padding required, depends on the other fields. So what are the other fields? One of the other fields is the next header field. You know the purpose of it, right? The next header should indicate what should be the protocol processing the packet after the ESP protocol processes it. So still the same standard is followed. After the IP header, the ESP header protocol will process it, and then the TCP protocol should process it. So the next protocol field should be still 6 if you want TCP to be the transport layer protocol to process it. And then you have here the authentication data. So the authentication data is what? It is?
The hash value?
Is the hash value. So it's again the same kind of authentication, the hash value that you compute for authentication header. Same way you have a key hash function that takes a key and the message. So here the message is everything that is part of the payload, right? But again, I think that change cannot be part of the authentication computation. So the only fields that are considered for authentication computation are like the one in this dotted line, which is basically, let me try to extend this. So starting from here, The SPI, the sequence number, the TCP header, the data, the padding value, and the padding length, and the next TCP. Everything within this blue dotted line is used to compute the authenticated data. Okay? And what is used to compute the encrypted data? The LO field. Okay? Now, so that's why you may be wondering, where is the encrypted data? We saw where's the authentication data, right? The authentication data is following this, right? So where is the encrypted ciphertext? This is your ciphertext. So you don't include the TCP header and the data in plain text. You compute the ciphertext by using the encryption algorithm you agreed upon for the security association. So the whole thing, everything in LO is basically a ciphertext of what? The TCP header, the payload, the padding length, the next TCP header, and so on. Okay, next header. So that provides you confidentiality, because if someone tries to, so if you want to kind of prevent the, protect the confidentiality of your.
Dr. May, I hate to ask you to repeat that. Everything in yellow is the what computes the authentication data.
No, everything LO is used to compute the ciphertext, which means for confidentiality. Alright? And so the ones that are used for, as I showed just now, the ones that are used for confidentiality are also used to compute the authentication. You see here what includes the blue dotted line.
Okay.
The blue dotted line starts from here, includes all the things in LO, as well as includes what? That's it. So it includes all the things in LO. In addition to that, it includes the first two SPI and sequence number. So those fields are used to compute the authentication data. The ones in LO are used to compute your confidentiality data. This is for ciphertext.
Okay.
Okay. And in addition to those fields, the SPI and sequence number are used to compute your hash value.
Okay.
Okay. So what you send is actually the encrypted version, not the plain text, the ciphertext. So that way you provide the confidentiality. Okay. So that's how ESP header is designed. Okay. So it provides you all the three, but it is an overhead to compute all of them and include, right? So that's why only if you want confidentiality, you go for the ESP header. If you want this integrity and authentication, the authentication header is very simple. So just go for that one. Okay? And the padding is needed if you compute the ciphertext, or if you compute the hash value. If nothing, if you cannot make it to the 32-bit boundary, right? So that's when we have to include padding. Okay, so you do some padding, means some dummy bits, bytes, to make sure the length of the contents, the ESP header is multiple of 32 bits. Okay, and how many 32-bit quantities you are adding, how many bytes actually, how many bytes you are adding here will form the padding length. Right? That's not a main issue. One thing that is, now what is the character of ESP header? The ciphertext is computed on the TCP header as well as the data and the other fields. What are other fields? The next header field is the padding length. So that's one characteristic. This is different from the authentication header. The authentication header is computed on fields that don't change. The confidentiality thing is also computed on fields that don't change, but the number of fields that you use for computing confidentiality is very limited as the TCP header of the data, whereas for authentication you include several other fields also. Right? And also you should notice the fields that you use for authentication, computing the hash value, the AH header, the authentication header is different from what is used for the ESP header. In the authentication header, you notice everything in this LO and the IP header also used to compute the hash value. Whereas in the ESP header, nothing in the IP header are used to compute the hash value. Only the SPI and sequence number are used to compute the hash value. So no field in the IP header is used to compute the hash value. So that is something different between the two headers, the ESP and the AH protocols. Okay? Is that clear? So you see here I haven't shown anything here to be part of the authentication process. So you may be still wondering, if nothing is used, if no field in IP header is used to compute the hash value, if someone sends from a fake IP address, how can it be captured? How can the receiver detect it?
Say that again.
If no field in IP header, right, like the IP address, source IP address is not used, right, here for the ESP case to compute the hash value, how can the receiver still just find out if it gets a packet from the real machine or from spoofed IP address?
Can you trace the IP address?
Yeah, you could trace, but I'm telling you, because if someone can spoof using ESP, it won't be popular, right?
So they can change the IP address?
Yeah, someone can, including like as a packet gets forwarded, or even like someone can send from a spoofed IP address someone and make it appear to come from this, right? So how can the destination detect it if the IP address is not used to compute the hash value?
Can they sit along like a computer?
The hash value has to compute the hash value. You have to know the key, right? So
Right.
you won't. If you're attacker, you shouldn't know the key. Only the real source and destination user can know the key, or the host will know the key, right? So to compute the hash value, what's the keyed hash value, right? Which means you have to know the key as well as the message. So the message is available to the attacker, but you won't know the key. So unless you know whatever the keys you agreed upon for the security association, you cannot really send from a spoofed IP address, right? Similarly, confidentiality. So we have to know you may know what algorithm is being used to compute the ciphertext, but you don't know the secret key used to compute the ciphertext. So that way it provides confidentiality. Okay? Okay? Anything else?
So would that be one of the first steps that they would have to do is compute the hash value, right?
To compute the hash value is not the first step. To get to that point, they have to agree. I think I know what you're asking for. The first step in IPsec establishment is to do this internet key exchange process. This is where they exchange the public key certificates to know about the public key of each other. So once they establish the association, they have to establish a security association.